Hello students, so in this lecture we will be discussing about acoustic emission sensors. Now there are temperature sensors which we have discussed previously, uh, which is based upon say a direct contact made with the system and the probe, which may lead to a change in conductance or a change in the luminous intensity, whatever it might be. Now, there are some systems or some conditions or some situations, experimental situations, where the direct probe contact with the system cannot be established. Like when we are dealing with very low temperature systems, like which are known as cryogenics, uh, where the use of liquid helium and nitrogen is taking place, and with temperatures which are close to the 0 Kelvin, uh, in relation to properties of superconductivity and other studies. And also there are situations where the temperature is very high, like in nuclear reactors. Uh, so there are some situations where we need to think of some alternative where the pressure or the temperature can be measured. The alternative comes in the form of an acoustic temperature sensor. Now, the basic principle of these type of sensors is the change of speed of sound with respect to temperature. Now, the speed of sound in air is very based upon the temperature and the medium. Like in air, the speed of sound at 20 degrees centigrade and 1 atm pressure is 343 meter per second, whereas in the same condition the speed of sound changes to much higher, 1482 in case of water, and in case of steel it goes even further, 5960 meter per second, and in vacuum the sound cannot travel because it always needs a medium to travel. Now, this principle has been applied to form an acoustic temperature sensor, which is schematically shown here. So, from the diagram, what can be observed is that there are mainly three aspects of this sensing system. And the first one is the transmission, the next one is the propagation, and third one is the reception. And the transmission and the propagation, and what do we transfer here? The transmission of what? So basically we are transmitting ultrasonic waves, which are being transmitted at a temperature of about 100 hertz. So 100 hertz temperature, 100 hertz frequency, about 100 hertz frequency of waves are transmitted, and they travel along the tube, which consists of dry air, and it gets received. Now, both of these transmission and receiving systems are associated with piezoelectric material, and so the whatever speed of sound or the change of speed is observed based upon change of temperature in the system, it gets reflected in terms of electrical signals. Now, there is one more aspect to it, is since both of transmission and reception they are based upon piezoelectric effect, the system is made in such a way that these two piezoelectric uh, devices are decoupled. By decoupling, we means that one is not associated with other one. will not get affected with the other. Now the factors, now the speed of sound is mathematically is expressed as root of elastic modulus versus the density. Okay, and so apart from density and elastic modulus, there are certain external parameters. These are related to the internal parameter of the material, whereas the external conditions like pressure, temperature, and humidity may also affect the speed of sound. And one of them is temperature, which is being utilized here to show the acoustic temperature sensing mechanism. So the ultrasonic waves are transmitted through the transmitter, ultrasonic waves, and the change of temperature may cause change in the velocity of the ultrasonic waves, which will affect the piezoelectric frequency, and it will be received as a change in signal. So it will give us the value, or it will sense if there has been change in temperature in the system. Okay. Now, in the case of gas, the velocity of sound is again related to the adiabatic constant and the molecular weight of the system. So a quantitative estimation of the temperature also can be made by this acoustic sensor emissions. Now the next is using a PN junction as a temperature sensor. Now the PN junction, we all know there is a forward bias and there is a reverse bias condition. So in the forward bias condition, usually the change in voltage it has a negative coefficient with respect to the resistance. So an increasing of the voltage may lead to this type of effect. You can see there are two temperatures taken. So as you increase the width, this temperature coefficient value, the slope value, it actually reduces. And this is more active in the forward bias junction. In the reverse bias junction, it is quite constant. So another advantage with these type of sensors, temperature sensors, is that with increase in temperature, the relationship between I relationship, it becomes linear. Not here you can see it's not linear, but it is going towards a linear relationship. So that is good for sensing. So one of the advantages. Now the relationship, this is quite a well-known equation, that is the relationship between the current and the voltage, and the relationship between the voltage and the semiconducting material used is the following, where this Na and Nd are new additions to the voltage equation, where and these are basically the acceptor concentration and the donor concentration. Ni is the intrinsic carrier concentration. So a typical current voltage characteristic block looks something like this, where on increasing the temperature, you can see these are the effect that is happening. So it rises very sharply and it then saturates, and the same trend is being followed for all the temperatures here. Okay, that's it.